In the previous video, we defined double integrals and iterated integrals over a rectangular region and used Fubini's theorem to show that for continuous functions, all of these integrals were equal to each other. And so we were able to use the iterated integral to compute the value of a double integral. In this video, we're going to extend what we did in the previous video, including Fubini's theorem, to non-rectangular regions. Right, so to do this, we're going to start with a function f of xy that's defined on a non-rectangular region R. Right now, we don't really care what the region R looks like other than it being non-rectangular. We are going to impose some conditions on that in a moment. And so we want to make two assumptions, and we want to assume A, that f is continuous on R. Right? This is not that broad of an assumption. If we have a polynomial, for example, it's continuous on any region R, and so are a lot of other functions. But the bigger assumption is the following. We want to assume that the boundary of R is going to consist of a finite number of consecutive curves, each of which is the graph of a continuous function on a bounded interval. Right, so this assumption really just says that the non-rectangular region R that we're defining our function on is not very weird. There are certain weird regions that double integrals and iterated integrals fail to work on. But as long as we follow some obvious facts about making sure each side of the boundary of our region is a nice curve, a line segment, a parabola, some smooth polynomial curve, something like that, then we'll be able to define all of this. And so I want to give a name to this second condition just so I don't have to refer back to it and write all of this again. And so for purposes of this class only, this second bullet point, we're going to say quickly as saying R is nice. Right? So of course that is not a technical term. I'm putting it in quotes for a reason. But just so when I say, like, suppose we have a function that's continuous on a nice region, this is what I mean by nice. I don't want to have to repeat this whole paragraph every time. So if we're given a nice interval or nice region R, then the double integral over R of our continuous function, f of xy dA, is defined similarly as it was over rectangles as a limit of Riemann sums. Right? In fact, a double limit of double Riemann sums. But we're not going to go over that whole process. It looks very similar to what we did before. And so at this point, given the region R being nice, that allows us to be able to adapt the previous calculation to this new region. And we then also get a general version of Fubini's theorem. Right, so this is our most general version. It's not over a rectangular region like the previous one was, and it extends in the obvious way. Right? So our assumption here for this theorem is we need a function f of xy, which is continuous, over a nice region R. So we have both of our assumptions that we made previously taking effect here. And if this is the case, then the double integral over our nice region R of our function f of xy dA will equal either of two iterated integrals. And so we have to be a little careful here. It will either be the integral from c to d of the integral of h1 of y to h2 of y of f of xy dx dy, or it can be the iterated integral from a to b of g1x to g2x of f of xy dy dx. So the big difference in the iterated integrals presented in this version of Fubini's theorem is that the inside integral has limits of integration that involves a variable. Now, if we think of a region R with rectangular, then thinking of it in either direction, either in terms of x or in terms of y, both of those limits are going to be constants because each of the sides of the rectangle, the vertical sides will be x equals a number a and x equals a number b, and the horizontal, the top and the bottom will be y equals c and y equal d. And now, depending on which integral that we use, we will have, if we have a non-rectangular region, we do not have every value between two values of y or between values of x. We have every value between two curves of either x or y, depending on which version we use. And so it is possible that h1, h2, g1, g2, at least one of them are constants, right? But that doesn't have to happen. It depends very much on the region itself. Right? And so as we see with some examples, the difficulty in double integrals and iterated integrals is not in the integration itself. In fact, that most people find fairly straightforward. The difficulty comes in getting the integrals set up properly. With rectangular regions, that's incredibly easy to do because you're going to have to be given the sides of the rectangle, and those correspond to the values, to the four limits of integration. And so when we deal with non-rectangular regions or nice regions like this, we have to work a little harder to find the limits of integration. We have to look at the various cross sections and what curves these cross sections are lying between. And so that's where a lot of the work comes in. And of course, if we don't have the proper limits of integration, then our computations are not going to be correct. And so we're going to look at a few different examples of different kinds of problems involving these, and looking at how we can come up with the appropriate limits of integration before we go to integrate the functions. All right, so for our first example, let's say we want to evaluate the double integral over our region R of the function 5y dA, right, where R is the region bounded by the curves y equals 3x squared and y equals 2 plus x squared. All right, so first thing really quickly we should run through is to make sure Fubini's theorem applies. So the function 5y is continuous everywhere, so that's not a problem. In our region, it's bounded between two curves. We're told explicitly that here. And so we know that this is a nice region. It has a finite number of curves, in this case 2, and each of them are nice continuous functions. And so Fubini's theorem will apply. So in this case, we're actually given the region R as the region between two curves. And so a lot of times in such cases, it's helpful to have a picture of the region so that we can set up our limits of integration appropriately. Right, so I'm going to draw a quick sketch of these two functions. Right, so I know y equals 3x squared is going to look a lot like a normal parabola, but it's going to be stretched vertically by a factor of 3. Right, so it'll look something like this. Right, so let's say this will be y equals 3x squared. Right. I also want the function 2 plus x squared, so this will be the standard parabola y equals x squared, but pushed up 2 units. So maybe it'll look something like this. Right, so this is y equals 2 plus x squared. And the region we want is the region between these curves, which is this region in here. Right, so this is region R. So what we would like to do is describe these regions in terms of limits of integration. And so one thing that we could do is we could start by finding the intersection points of our two curves. And that would be sort of our boundary on the x-axis. And so to find where these curves intersect, we just use algebra. I mean, it's probably pretty clear actually what they are. But let's say we weren't able to just look at the functions and see what values of x would give us equal values. We could always set the functions equal to each other. So 3x squared equals 2 plus x squared, and we can solve this for x. So this just gives us 2x squared equals 2. X squared is 1, and therefore x is plus or minus 1. Right? So we know our intersection points are here, and so I have negative 1 on the x-axis, and I have 1 on the x-axis as well. And so our region lies between x equals negative 1 and between x equals 1. Right? So we have negative 1 less than or equal, or negative 1 less than or equal to x less than or equal to 1. And our y values lie between our two curves. And so I know y is always going to lie above the black curve, which is 3x squared, and below the red curve, 2 plus x squared. And now notice these two conditions will give us the limits of integration for an iterated integral. We have the x lying between two constants, and we have the y value lying between two functions of x. And so this is exactly what we need for one of the iterated integrals mentioned in Fubini's theorem. Right, so I want to compute the double integral over r of the function 5y dA. And so this will be, by Fubini's theorem, the integral from negative 1 to 1 of the integral from 3x squared to 2 plus x squared of that function 5y dy dx. Right, so this is just substituting everything into our integral, and now we need to compute this integral. So we need an antiderivative of 5y in terms of y, so that would be 5y squared over 2. And we're going to evaluate that from 3x squared to 2 plus x squared. Right? And so I'm going to actually just bring that 5/2 out front. It's a constant, so I just have to evaluate y squared. So we're going to have 2 plus x squared squared minus 3x squared squared. Right, so I assume you can do the algebra to simplify this function here. And if you do, and you do it correctly, you'll get 20x to the negative 20x to the fourth plus 10x squared plus 10. All right, so I'm skipping that just for sake of space on the slide, but it's really just distributing, squaring out everything, distributing the 5/2 and so on. So we have this integral, And now this is a relatively straightforward integral. We're just going to integrate with anti-differentiate with respect to x. So we'll have negative 4x to the fifth plus 10 thirds x cubed plus 10x evaluated from negative 1 to 1. All right, and so we end up with negative 4 plus 10 thirds plus 10 minus the quantity 4 minus 10 thirds minus 10. And if we do the arithmetic here, I believe we end up with 56 thirds as our final value. Right? And so this double integral is equal to 56 thirds. Okay. Now, when we did the examples with rectangular regions, I did ask you to compute the region using the other iterated integral. And if you did that, you saw that there was about the same level of difficulty. In this case, it would be a lot harder to do in terms of, or a little bit more work, I should say, to do the other iterated integral. We would have to find boundaries for y, which were constant, and that would be possible. We could start, if you look back at the region, the y values range from y equals 0, which is the x-axis, up to y equals 3. That's the y value of those intersection points. But then we would need to write each of the curves in terms of x in terms of y. And so we would have to compute, we'd have to rearrange our equations for the curves, and we'd have to compute what they are as a function of x in terms of y. And that's a little bit more complicated to do, although possible. And then to do the integral that way. So oftentimes one of the two iterated integrals will be easier to do than the other. And so usually it's worth taking a moment to think about what you do before you actually do it to make sure that you don't have to sort of go back to the beginning and restart. Okay, so let's look at another example. And in this example, let's say we wanted to evaluate an iterated integral. So the iterated integral from 0 to 1 of the integral y to 1 of the function sine x over x dx dy. Right? So we're not looking for a double integral here. We're looking at actually just this iterated integral. Right? So this one seems easy enough. The first step, we're differentiating with respect to x. So we just need to find an antiderivative of sine x over x. Right? So I'll let you have a few seconds to think about how to find an antiderivative of sine x over x. All right, I'm going to assume that you have no idea how to find an antiderivative of sine x over x. And that's okay, because neither do I, and neither does anybody else who's ever lived, because this particular function causes a significant problem. And the problem is there is no elementary derivative, or elementary antiderivative of sine x over x. Right? So it doesn't matter how long we would sit here and look at it. There's no possible way for any of us to come up with an antiderivative for that function with respect to x. Right? And so as written, this integral just cannot be done by hand. However, part of Fubini's theorem, it doesn't just say that the double integral can be written as iterated integrals. It says that the two iterated integrals where we differentiate with respect to one variable and then the other, those two integrals are actually equal to each other. And so what we're going to do is we're going to consider the region that's implicitly being used in this integral, and we're going to try to swap the variables of integration. Right? And so if I look at, if I take the two integrals and I sort of rewrite them as inequalities, I know that I want x, the variable x, to range from y to 1. So I want all values of x greater than or equal to y, but less than or equal to 1. and I want y to range from 0 to 1. And so if we try to graph this region, I know y equals 0 is the x-axis, and I have y equal 1 up here. So I want the values of y to live between 0 and 1. And then x, I want to be less than or equal to 1, so I want it to be to the left of this point 1 on the x-axis, but I also want it to be above y. And so when we do this, we want to consider x equal to y. So I'm going to go ahead and draw in this line. This is the line y equal x. And so what we want, I'll just draw the dot over there. This is the point 1, 1. We want all the values where y is between 0 and 1 and where x is greater than or equal to y, but less than or equal to 1. And so that describes this region here. Right? So we want, and you can check that if you look at it carefully. We have every point in that region is going to satisfy y being between 0 and 1, and it's also going to satisfy x being less than 1 and having an x-coordinate bigger than y, the y-coordinate. And that's exactly what our region was supposed to be. And so this is our region here. Now, if I want to look at the other iterated integral, what I need is I need x to be defined by constant limits and y to be defined in terms of variables. And so what I need x to be between two constants. So again, looking at the picture, I see x is going to have to be between 0 and 1. And then y, we want limits here, and now we're allowed to use functions of x. The y values are always going to be between 0, so they're always going to be greater than or equal to 0, and they're going to be below this line y equal x. So in other words, I want y to be less than or equal to x. Right? And so notice that these two inequalities describe the exact same region as those two inequalities. It's just that we've sort of switched which variable is set between two constant values and which variable is bounded by a function of that second variable. Right? And so this allows us to rewrite our iterated integral that we're given in terms of the other iterated integral where we differentiate y first. Okay. So we wanted to compute the integral from 0 to 1 of the integral of y to 1 of sine x over x dx dy. And what we just saw was that we can rewrite that region as the integral from 0 to 1 of the integral 0 to x of the same function. We haven't done anything with the function, but we have changed the limit of integration. Okay. And so these two integrals here are each defined by the different pairs of inequalities that we had on the previous slide, which we saw represented the exact same region. Right? The nice thing about this integral is that we can compute an antiderivative of sine x over x with respect to y. Right? With respect to y, sine x over x is just a constant. Right? So we have the integral 0 to 1. We have sine x over x. That's a constant in terms of y times y, and it's going to go from 0 to x. Right, so maybe I'll put that in parentheses to kind of keep that separate. Right, so we have the integral from 0 to 1. When I substitute x in for y, we get sine x over x times x, and the x's will cancel, so we just have sine x remaining. And when I substitute 0 in for y, we just get 0. And so what we end up with, in the other case, we had an impossible integral to compute. And in this case, we easily do the antiderivative, we evaluate it, and we get the integral from 0 to 1 of sine x. Right? And so this is just going to be negative cosine x evaluated from 0 to 1. So we get negative cosine of 1 minus negative cosine of 0. So that'll be plus 1. And so if you wanted to rewrite this as 1 minus cosine of 1, we could, although of course not necessary. But this is the value of this particular integral, which we obtained by reversing the order of integration. Right? Now, the one thing I will point out before we go on to another example is whenever we have to switch order of integration like this, you do need to pay attention to the region. You can't simply just change the x to the y and flip the integrals around. Notice here that even though the outer integral remained 0 to 1, the 0 to 1 means something different in each case. On the integral on the left here, that 0 to 1 means 0 to 1 along the y-axis. And this 0 to 1 means 0 to 1 along the x-axis. So even though those outer integrals are looks unchanged, we are actually measuring something different with each of these.